Welcome to the House of Intellect. I'm RITURAJ Mishra. I bring to a presentation a paper that I worked on for studying the electrochemical corrosion behavior inside coatings in cathodically polarized pipelines that includes CP shielding and differential aeration corrosion. Well, dear friends, I am Senior Manager Mechanical Maintenance currently with pipelines in BPCL, and my areas of specialization include integrity inspection, risk assessment, corrosion management, external, internal interferences, inline inspection, mainline repairs, and corrosion audits. I'm very thankful for the chair to have introduced me. And currently, I am the Young Achiever of the Year in Oil and Gas Industry in India, awarded in 2019. With this, I'll proceed to the paper. Well, I will start with a small point. Rust is must. We can measure it, we can test it, we can halt it, we can arrest it, we can gather it, we can weigh it, we can coat it, we can spray it, we can pick it and drop. We cathodically protect it with a strong belief we can stop it. Dear all, corrosion is never for maintenance. It is always prevented at the first place. With this strong belief, let's go to the paper. Well, a question comes up. Do you have efficient corrosion monitoring? Now, the word efficient is very important here because if you are monitoring your data only to not to see, hear, and say anything which may go against you, then it's not an efficient corrosion monitoring team. What matters here is, do you monitor corrosion for data? Do you monitor for compliance to standards? The time is now that we monitor for evaluation and we monitor for information, because that's where the real data arrives. The decision making is very critical. Here, if you see, everyone seems to assume that a PSP value of minus 1.2 certifies protection. Is it correct? Is it the only basis? I'm here to challenge the very same thing because I have done a lot of study on the same, and I can claim that corrosion still exists with ICCP in place. Very tricky, right? So let's go into the depth. I hope the audience believes time is now to execute SIP in corrosion mitigation, to shift from data to information, to enhance capacity to capability. Like we can have a lot of engineers with us looking after corrosion, but are they capable to handle the problems or they are just numbers? And finally, the time is now to transit from being efficient to being effective. Let's talk about corrosion inside coating. I hope you can relate yourself to these pictures. These are not new. You might be doing corrosion repairs, coating repairs, and you would have observed that in spite of having cathodically protected pipelines, you will see rusting in between the coating and the pipe when you go for opening them. How at all it happens? So this paper is all based on the site feedback and lots of screening activities on corrosion, a brainstorming session, then case studies have been taken up, and finally the inferences have been converted into the parameters which are very critical for all of us to know what controls corrosion. The highlights of my presentation, introduction, and then the current corrosion issues that we are facing, the concentration cell corrosion to a greater extent, and the methods of control and prevention. Finally, the conclusion. Dear all, what desire we have when we buy coatings for our pipelines or apply them? It needs to be effective electrical insulator, good holiday and abrasion resistance, good adhesion to pipe, ease of repair and applicability, non-toxic interaction with environment, good soil stress and penetration resistance. Types of pipeline coatings mostly involve coulter enamel, fusion bond epoxy, 3-layer polyethylene, 3-layer polypropylene, and heat shrinkable sleeves. What happens when a coating deteriorates? Basically, the oxide dissolution at metal coating interface, the mechanical interfacial failure, and the disruption of the polymer metal interface by the hydroxide. I hope the audience is aware because these are very simple phenomena which happen because of the coating deterioration. Now, when a coating goes for disbondment, a lot of factors which I could identify have been tabulated here. One of them is the soil type, the topography, the percentage of clay, the drainage, the seasonal variations which account, including the weld position of the pipe, the coating surface preparation, let it be in the field or in the factory, and further the aging of the coating, the external forces which are at play, and the type of the coating. These are the few factors which I could attribute for the coating disbondment. Let's talk something about cathodic shielding. This is just a general presentation to brief the audience that this is what the cathodic shielding is all about. The red area is the zone wherein you are getting the cathodically protected current, but the white area inside this is the area which is not getting anything. Now, the trick comes here. The corrosion with ICCP in place. Why? Because there are coating defects, the holidays, the disbonding. There is moisture from the soil which is in contact with the metal surface always because the pipelines are buried in the ground. And the cathodic protection current is expected to reach to the holidays in the coating. Cathodic protection is shielded sometimes and is not sufficient to ensure a current density to carry out the required polarization of the metal. So what happens here? This is a simple case wherein perps, I hope you are aware, perps are small coating patches which are used during projects to fill up the holidays which we observed in holiday survey in the laying part. These perps are nothing but a separate layer of coating rubber which is not equivalent to the mother rubber. So what happens is the coulter coated pipes are sometimes provided with perps and the perps are disbonded with aging because they don't get adhesion properly because these are two different coating materials. So this has given up to corrosion. Corrosion inside heat sinkable sleeve at the welds. You can see that a cathodically protected pipeline is having a weld wherein the heat sinkable sleeve was applied in the field. And instead of having cathodic protection, severe amount of corrosion has happened in and around the weld area, which is observed only when we tear up the weld, and this was detected in the ILI. Case study 3 is all about water inside field joint coating installed on site being replenished through holiday. So again, water has come inside and it has started corroding the pipe. And finally, these are some of the snapshots which you got from the field because of the cathodic protection shielding phenomena, wherein the current could not penetrate inside the holidays in the coating. So, what are the 5 different root causes that I could identify with my works? First is applied cathodic potential, the impact of it. Second is the resistivity of the solution, which is there in and around the pipe. The holiday size matters a lot for the coating. And finally, there is a crevice thickness also matters a lot. In my case, it did. Direction of flow of electrolyte is a matter of concern, but we don't have any control over it. Let's talk about the first parameters. Effect of applied cathodic potential. Gentlemen and ladies, still is polarized by the applied potential. We hope that we all are aware about the same. What does the cathodic protection do? It just polarizes the pipeline by polarizing the ground potential around the pipe. And in that process, the oxygen is consumed and the pH increases, creating an alkaline environment. Now, the oxygen content in the water occupying a crevice and holiday is equal because of the reaction which is driven here, that is O2 plus 2H2O plus 4 electrons gives you 4OH minus. This is the alkaline solution which is created. Now, the crevice and the holiday are having equivalent concentration of oxygen. In stage 2, what happens is the corrosion reactions now start. They specialize mostly in the anodic area, which is the crevice in this diagram, which you can see, and on the cathodic area also. Now, in the cathodic area, the reactions are more dominant compared to the anodic area. Now, when we impact the cathodic potential, we see there is a crevice development which is happening because of the corrosion products which are forming over time because of the polarization phenomena which is taking place outside the holiday and the rusting which is taking place inside the crevice. This is a localized acidification in the crevice. The corrosion products further seal the crevice and you get to see that the accumulation of positive charge in the crevice attracts negative ions to form chlorides. Now, this is the concern here because if you go to the next stage, you know what happens whenever there is a power failure, the panels are supposed to not deliver anything. And in that case, what happens is the interruption of the CP current happens. And this drives Basically, a interruption circuit creates a phenomena wherein it removes the driving force that is very much important for the cathodic protection. Now, during interruption, the holiday, the anode, will try to equilibrate by neutralizing the solution between the device and the holiday. So what happens in this phenomena is the outside environment in the holiday is already polarized. The inside one is not that polarized, but because of the power interruption, the inside and outside try to neutralize. During application of the cathodic protection, again after the interference, anode solution becomes less alkaline because the equilibrium was established and suddenly the current was restored, and cathode solution becomes more alkaline. So this proves that the rate polarization at the cathode is comparatively more compared to the anode. Anode is the crevice area. Now, when you see the chemistry changes inside the crevice, basically the oxygen level inside the crevice, the depletion of oxygen in the crevice leads to a acidic condition in the crevice, and further to that, it tends to create an aggressive ionic species, which form a layer of deposit on the crevice. And further, you can say that the movement of ions from the outside environment to the crevice won't happen as faster as it used to be because of this formation of aggressive ions. Now, in this diagram, all I wanted to present is, if you can see, there is a oxide layer on the cathode, but the anode area is the holiday area which is exposed to the bare environment. And in that environment, you can see there is a movement of interactions between various ions. And that is nothing but an aggressive corrosion which is taking place inside the crevice. Well, now what is happening? The higher negative potential increases the hydrogen gas evolution, which we are talking about, breaking down the adhesion between the coating and the pipe metal, because this hydrogen basically bonds your coating from the pipe. So the iron dissolves as a reaction at the anode, and oxygen consumption happens at the holiday. And because of that oxygen consumption, what you get to see here is a rust hole. We should all believe that this Fe2 plus H2O creates FeOH, which is very well-known reaction, and the rust which is formed on the surface now is basically driven by the oxygen consumption at the holiday. One more scenario that I have observed is when a pipeline is buried in the ground, you can see the bottom 6 o'clock position has got very less concentration of oxygen compared to all other three sides. This is also driving a differential erosion corrosion, and that's why you would see most of your rusting happening at the bottom if at all you have perps or disbondments at the 6 o'clock position. This is one of the key factors. Now, we'll consider the second factor, that is the solution resistivity. Now, you all must be aware that resistivity is nothing but the opposite of conductivity. Now, in case of cathodic protection, all that matters is the flow of the ions. The higher is the resistivity, the lesser will be the flow of current, and the less impactful will be your cathodic protection systems. So, the low resistivity waters gain a deeper penetration into the crevice and thus achieving cathodic protection inside the crevice at a much faster pace and thus ensuring a correct cathodic protection implementation. Third thing that we have observed is the effect of crevice thickness. Now, I wonder how many of you are aware that a crevice, the tighter it is, the faster is the polarization, because I have already told you that the cathodic protection not only polarizes the pipeline, but also alkalizes the ground potentials, the groundwater potentials. So if we have a tighter crevice, the polarization is much faster, and a thicker crevice will have a lesser and slower polarization rate. Hence, the amount of solution which is expected to be contained in these crevices are driven by the tightness of the crevice. Next is the size of the holiday. Now, the size of the holiday is directly proportional to the crevice polarization. It's a simple thing which everybody will understand, that if you want to polarize a certain metal surface, the higher is the exposure, the better it is. Finally, the effective direction of flow of electrolyte governs the movement of the corrosive species. Now, here I would like to just present you that suppose your pipeline is in a terrain when it is going from the top towards bottom. Now, the flow of water will basically move along the pipeline through the path of the coatings. Now, it tries to penetrate in the holidays and go deep inside. Now, as long as your pipeline is along the terrain and water is going inside the coatings, it will try to ensure a good cathodic protection system. But the moment the seasonal variations occur, the outside electrolyte is no more available in the summer season, and water is already there inside the coating, which are gone inside during the rainy season. Now, because of that, the water content inside won't be able to be protected because the cathodic protection current has a barrier now. It is not able to establish a continuity between the outside and the inner atmosphere. I have established a rule of thumb by going through some lot of literatures on the online available portals that if your pH is less than 5.5, the corrosion rate is very, very severe. Resistivity less than 2000, conductivity more than 0.4, and like that, moisture more than 20%. So these are all things I wanted to present to you as a part of the rule of thumb. Finally, how do we mitigate such issues? Well, there is no simple answer to it, but yes, I have just jotted down certain points which may be useful for the audience. First is the ILA inspection should be done on proactive basis. Second thing is dedicated refurbishment of the shielded coating integrity areas. See, the shielded coating integrity areas cannot be solved by increasing your cathodic protection current. All that matters is you need to do periodic refurbishment of the coating integrity in the shielded areas. Further, the coating surveys, when they are executed by the site technicians in the field, see, an on-the-line survey across the ground layer does not give you a correct indication of your coating health. But carrying out the coating surveys at least eliminates to a bigger extent having failure. Finally, none of the coating products are bad. It is all about the skilled and procedure application of the coating in the field that helps you gain the advantage. Concluding my presentation, I fully feel that the audience will agree with me that the CP modifies groundwater solution rather than just polarization. CP current need not flow direct to the disbonded areas, but it can still protect the areas. Aerated water's periodic replenishment makes CP ineffective because it is accountable due to the seasonal variations. And finally, skilled and procedural application of coating should be done to avoid any damages. It would be very nice on my part and also on the part of the authors whose articles and journals I referred while doing my research on the field. And I'm very thankful to them, in particular, Mr. J.J. Pedromo's paper, Buchanan for toilet stock shielding, and finally, mitigation of external corrosion and buried pipelines manual from Canada, that is the Association of Petroleum Producers. With this, the key takeaways I would just like to reinforce in the mind of all of you is applied cathodic potential, solution resistivity, holiday size, crevice thickness, and direction of flow of electrolyte are the key parameters that control your corrosion inside coatings, even with ICCP applied. So with this, gentlemen and ladies, I'm very happy to energize you and I'm welcome to any questions. Thank you.